Hello everyone, my name's Jordan Beim and I'm a postdoc at the University of Minnesota, and in this video I'm going to go over the basics of the Vocoder module that comes as part of our signal processing toolboxes. Most vocoders used by researchers today operate totally in the acoustic domain, using signal processing to degrade an input sound in a precise way that mimics the loss of information that occurs as a result of perceiving sound through a cochlear implant. This vocoder is different than most in that it is a biophysically inspired model of how the current pulses generated by the implant spread throughout the cochlea, activating neurons. Instead of taking sound as its input, we can feed it the electrical pulse data from our implant simulation directly, and it will produce a degraded sound that will help you as the contestant understand the effects of your new sound processing algorithm on a typical implant user. The simulation can be broken down into a few major steps for the purposes of a high-level overview. First, we physically simulate the electric field spread from each electrode. Overlapping spread from adjacent electrodes allows for advanced features like current steering to be simulated. Then, we estimate the probability of neural activation to these electric pulses by integrating electrical activity at a large number of simulated neural locations over a short time window. This process likely smooths out most short timescale effects, like dynamically adapting the pulse rate. Simulated neural activity is then summed across the neural locations and used to modulate a series of tones spaced across the range of human hearing, producing minimal envelope fluctuations for continuous stimulation when compared to a standard noise vocoder. The tones are then summed to produce the final acoustic output that will be judged by contestants. This final output should provide useful perceptual feedback to you as an algorithm designer. Since the contest is based on this audio, you should strive to optimize the experience listeners have while listening to the vocoder. As I mentioned previously, the vocoder is provided to use as a helpful tool to listen to your results. Any modifications made to the vocoder will not be reflected in the judged entries. In the default toolboxes, before being processed by the vocoder, the electrodogram is processed by a different module designed to help validate the output electrodogram against the requirements we have for all contest entries. These requirements help to constrain algorithms so that they produce outputs that would be more feasible to implement on existing hardware, as well as to help facilitate a smooth judging phase at the end of the contest. The validation function in our toolbox will also print some information to the console about the estimated similarity of your novel strategy to our default processing strategy when you are using it on entries ready for judging. The similarity to our default processing strategy of your algorithm will not invalidate your entry. However, a detailed code review process will be undertaken with the winners at the end of the judging phase of the contest. At that time, any entries that are not sufficiently novel will be disqualified. Our website will perform the same validation included in the toolboxes, which includes checking that the electrodograms must contain 16 channels, or rows in the data matrix, that match the 16 output electrodes in commercially available advanced bionics cochlear implants. Not all 16 channels must be active or contain electrode pulses for any given stimulus, but they must be physically present in the data matrix, even if they are all zero-valued. The output should be the same duration as the input. Our toolboxes internally resample any audio input to a final sampling frequency of 55,556 Hz. This final output rate must be preserved in order to prevent artifacts in the vocoder sound processing. In practice, what this means is that your electrodograms should have the same number of columns as your acoustic source has samples once you have resampled it to 55,556 Hz. If your algorithm involves time stretching or time compression, it will likely produce an invalid entry because the output will either be too long or too short. The electrode pulses must be charge balanced. This means that they have an equal positive and negative component, and the current within a channel must integrate to zero over time. This is a hard physical constraint on existing implant technology, and any new strategy must be able to adhere to this in order to be feasible in a real device. Our vocoder simulates a CI recipient with a threshold current level of 50 microamps and a most comfortable level of 500 microamps. Values in the electrodogram below 50 will not produce an audible percept at the output of the vocoder, and the sound level will saturate above about 600 microamp currents, meaning that Increases above that will not produce any additional increase in loudness. Generating outputs with levels outside of this range will result in generally poorer audio quality and should be avoided. Finally, the file name of your electrodogram file must begin with the file name of the acoustic source that generated it, followed by an underscore and EL-gram. What follows after the underscore EL-gram can be any informative descriptor you like. This is particularly important for judging because the website will reject file names that do not conform to this strategy. The naming convention is in place because it helps to ensure that your entries will be appropriately sorted into the correct categories for the judging phase of the competition. Our toolboxes save files with compatible file names and formats by default, so no special action is required if you're using our tools to produce your electrodograms. Before going over how to use the vocoder function and install the toolboxes, it's important to go over some important caveats that will be helpful when thinking about how to design your signal processing algorithms. Firstly, the vocoder is intended as a tool for you to listen to the results of your hacks, not an object that should be the focus of the hackathon itself. You shouldn't waste any time making modifications to the signal processing done in the vocoder because the submission website will use a static version with the same settings that we initially provide to you. There are also several important aspects of the electrodogram signal to which the vocoder is insensitive. We would encourage you to avoid spending time on strategies that produce the following manipulations. Changes in overall sound level. The vocoder explicitly normalizes the output level of all electrodograms because perceptual judgments, like those used in the judging phase of our contest, can be easily swayed by changes in overall loudness from sample to sample. Changes to the electrode pulse stimulation rate. The default stimulation rate is native to current advanced bionics implants. Real implant recipients seem generally insensitive to pulse rates at the rates used in the current implants, and the vocoder processing strategy integrates these pulses over time, but any increased loudness produced by using a faster pulse rate, for example, would be lost due to the loudness normalization at the end of the process. The order in which channels activate. In the continuous interleave sampling strategy, each channel provides stimulation at a unique time within one frame of audio to avoid current interactions between electrode channels. Changing the order in which the channels fire from our default strategy will be averaged out due to the frame length used in the vocoder and won't produce any audible difference in the perception for the judged entries. Finally, the vocoder is not capable of processing stimulation strategies that rely on different electrode pulse shapes with subtractive current interactions like tripolar or quadrupolar stimulation. Using these pulse shapes will not produce an error, but the electric field narrowing effect typically associated with these pulse shapes will not be represented in the output. In fact, instead of narrower electric field, multipolar stimulation will actually result in a more broadband neural response and acoustic output. Additive bipolar current steering approaches, like the one used by advanced bionics, are supported in this toolbox. These last two slides are meant to be cheat sheets that highlight the input requirements of the vocoder that we've already discussed, as well as a shorthand guide for using the vocoder modules as a standalone tool for listening to the output of your algorithms. Each slide is specific to a programming language, so you'll only need to refer to the one that matches your language of choice. We designed the vocoder module to work as a standalone so that it could be useful to groups who are using our toolboxes to do a lot of their signal processing, as well as any groups who might want to write all of their code from scratch. This means that the vocoder is designed to handle both raw data or files generated by algorithms. The first input to the vocoder is either a matrix of the electrode pulse data or a path to the file generated by our toolbox or your external code. If you write your code outside of MATLAB or Python, you'll need to save the electrodogram matrix as a compatible file type in order to submit it. The vocoders in each language differ slightly in their capability to deal with different file types out of the box. The MATLAB vocoder can only load .mat files, and if you're using MATLAB, you should ensure to save your output matrix as a sparse matrix to reduce the file size. The Python vocoder can handle a few more file types, including the .mat files, .npy numpy matrices, HDF5 binaries, and .npz compressed sparse column matrices created by SciPy, which are the preferred format for the Python vocoder. Regardless of the file type, the matrix of electrode data should remain the same shape, and it should be the only data element included in the file. The vocoder expects the .mat files to contain an array called EL-data, but the other file formats do not care about the name of the data array stored within the file when saving. As mentioned previously, make sure that the electrodogram files you create begin with the same file name as the source audio from which they came, which is especially important when you're processing entries to submit for judging. Please refer back to slide 5 for more details on these requirements. The vocoder outputs an array of floating point audio data as well as the output sampling rate so that you can play the processed audio through your own code if you like. An example of this is present in both of the demos. The vocoder can also save the audio output as a WAV file, which can be useful to compare the results from different manipulations to your processing strategies offline. There are optional parameters related to saving this audio so that you can control whether or not you save, what the file names are, and what the sampling rate of the audio files is. The format of these optional parameters differ slightly between the languages, but the functionality of each is the same. As we've touched on previously, the contest entries you submit to our website will actually be used as the input to the vocoder, so the sound output and WAV files that the vocoder can produce are purely to help you iterate on your designs, and you should not try to submit them to our website. As a final reminder, if your electrodogram files do not adhere to the points highlighted in red on these slides, they will fail the validation process when being uploaded to the website. Refer to either these cheat sheets or back to slide 5 in this presentation for the same reminders and more detailed explanation. If you're interested in learning more about some of the research that inspired the development and design of the vocoder, please check out the following references. A more detailed list of references regarding our understanding of the biophysics of electrical stimulation can be found on our website. This concludes my overview and installation guide presentation. PDF copies of the slides are available on our website as a static reference if you need them. And if you have any questions about our toolboxes or run into any technical issues while trying to install or use them, please reach out to us on the Hackathon Slack workspace. You'll be able to find a link to that on our website. Thanks for watching and good luck.